Power outages don't have to be scary. The Arduino emergency light system is the product you need during an outage. With the product features listed below, it'll light up your room during an outage when it is dark. You'll have remote access to an Arduino dashboard, accessible anywhere, where you can monitor voltage, grid status, and light status. The test input button allows you to test your system at any time to ensure it's working, and it is ready for an emergency. When the system is connected to power and plugged in, it will charge the battery, ensuring that the battery is maximized for when an emergency situation occurs, and the light will remain on for as long as possible. This battery voltage can be monitored from the dashboard. You'll now see the product work. A power outage has occurred. Luckily, our light will turn on and light up the room. This is because it has been disconnected from power and it is dark in the room, so the light is needed. When the lights turn back on, we'll see that our light is no longer needed and the light will turn off. Another feature of the product is a test input button, which allows us to check that the light is working during a non-emergency situation. As we can see, the light is working. If it was not working, we would have to replace the bulb. This is very useful to make sure your system is up to date and does not need replacing. Another feature of the product is the Arduino Cloud dashboard, which shows the grid status, light status, battery voltage readings, and the light value in the room read by the LDR. As you can see, right now the battery is connected and the voltage is rising as the battery is charging. This is shown by the green check mark on the grid status section of the dashboard, which indicates that it is connected. Since the grid is connected and there has not been a power outage, the light will not turn on when it is dark in the room. This allows you to turn on and off your lights without having your emergency light come on, and it is saved for emergency situations only. We can observe the light value readings in this situation. There is no light in the room, so the light value is reading 0. Although this is below the light threshold set to turn on the emergency light, the grid is connected, so the light will not turn on. When the main lights turn back on, we'll see a rise in this light value. The system monitors for power outages by checking for voltage drops. When the battery is no longer connected to the grid, there will be a significant voltage drop which can be detected. As we can see, the voltage just dropped from 13.1 to around 12.7 in a matter of seconds, which would indicate that the system has been disconnected and the light has turned on because of this. Thanks to these features, this product makes a great emergency light to be installed in any building. Installation of this system couldn't be easier. It comes in a compact black box with everything you need. On the top, there is a small hole which exposes the light sensor to room light and allows use of the test input button without removing the cover. The cord on the back connects the battery to the charger. The charger can be plugged into any 120 volt AC outlet, which is available in most buildings, allowing for easy install. This red light shows that the battery is charging and the charger is working correctly. We will monitor the battery voltage and see an increase in voltage as the battery charges. This flashing green shows that the battery has reached 80% capacity. Once it has reached 80% capacity, it will continue to charge until it reaches full battery, and it will maintain at this level. So the battery can remain connected to the charger without worrying about overcharge and maintain maximum battery until a power outage occurs, meaning the light will stay on for as long as possible. I will now review system design and connections. The entire system is powered by a 12-volt battery, which powers all components and the Arduino itself. As we can see, it is connected to the soldered breadboard at the power and ground positions and travels into the Arduino at the V-in and the ground. This powers the entire system, and the V-in will regulate high voltages. There is a common ground between the Arduino ground and the battery ground, ensuring that all components are connected to both grounds. Many components are powered by the battery, but are either receiving or sending inputs to the Arduino, meaning they need to be grounded to both grounds. The photoresistor, or LDR, which reads room light data, is connected to the battery power and also connected to an analog input on the Arduino through a voltage limiting resistor. This ensures that the Arduino is not damaged by high voltages being received through the analog input. The two resistors on the bottom serve as a voltage divider so that we are able to read voltage data from the battery without sending more than 5 volts to the Arduino. The resistor values chosen were 2.7K and 1K. These values were important, as we could see in the previous video, the battery goes up to around 14.6, 14.7 volts when it is charging. It is important to take this into account as we don't want to send more than 5 volts to the Arduino. As you can see, with the chosen resistor values, at a max voltage of 15 volts, we will never exceed 5 volts, sending only a max of 4.05 volts to the Arduino, ensuring we will never damage the Arduino. We take the voltage from the node between the two resistors to ensure we are getting the result of our voltage divider rule. This voltage is transmitted to the analog input at A5 pin. As designed, we will always be below 5 volts to ensure the Arduino is not damaged. The relay is responsible for turning on and off the LED. It is powered by the plus 5 volt pin on the Arduino and is also grounded to the Arduino. The digital signal indicating if the relay should be turned to normally closed or normally opened comes from digital pin 7. This digital pin sends either a high or low signal indicating if it should be normally closed or normally open functioning of the relay. When the relay is flipped to normally open, it will be powering the LED. When the relay is flipped to normally closed, it will not be powering the LED and it is not connected to anything at normally closed, and meaning the LED will be turned off. The conditions needed to send a high or low signal are programmed into the code, which we will look at later. However, it is fairly easy to say that a high signal will be sent when the grid has been disconnected and it is dark in the room, as the high signal will mean that we will flip to normally open and the LED will turn on. The final pin of the relay is the COM pin, which is connected to 12 volts from the battery. When the relay is flipped to normally open position, these 12 volts will flow through the normally open into the LED voltage divider rule. The purpose of this voltage divider rule is to limit the voltage and current going into the LED to ensure it lights up but does not burn out. When the relay is in the normally open position, the voltage will travel from the battery into the LED voltage divider, and then through the voltage divider into the LED. The resistor values chosen for this voltage divider were 1K and 3.3K. Since the LED is a 12-volt LED and the battery voltage can go above this, we do not want to send the entire voltage into the LED. With this in mind, the resistor values were chosen to ensure that the entire voltage from the battery was not sent to the LED. Through this voltage divider rule, we can see that the voltage going to the LED is about 75% of the total battery voltage. This ensures that the LED has enough voltage to turn on and is bright enough to light the room, however will not burn out at high battery voltages. Both the LED and the voltage divider rule are grounded to the common ground between the Arduino and the battery, ensuring that they are grounded properly and will work correctly. The battery charger and maintainer is a very important component of this system. It connects the system to the grid and allows us to check for voltage drops and rises for grid disconnection and connection. It maintains voltage when it is fully charged to ensure a fully charged battery at any time of emergency, and it charges the battery when the voltage drops below a full charge. The voltage rise indicates that the grid has been connected and the battery is charging again, which tells us that power has been restored in the case of an outage. The voltage drop tells us that an outage has occurred, as the battery charger has been disconnected from power and can no longer charge the battery. These are all detected in the code, which we will look at later. The power and ground of the battery charger are connected through the soldered breadboard to the battery to ensure that whenever the battery charger is connected to power, it will be charging the battery. The final component of this system is the test input button. It's connected to the ground on one side and a digital input from the Arduino on the other. It has a pull-up resistor activated in the code, meaning that the light will turn on when the button is pushed and it'll turn off when the button is not being actively pushed. Through thorough testing, it has been concluded that the components of this system work very well together to complete the intended purpose. We have observed that the light will turn on in the case of an outage and will remain off otherwise. I'll now review how the code works for this Arduino-based system. These are the 4 variables that are updating in the cloud each time and shown on the dashboard. First, we define the inputs and the outputs. The LDR input was the analog 0 pin, the LED output was the digital 7 pin, battery pin was analog 5, and these are the 2 constant resistors that we need for voltage calculations. The button was on digital pin 8, reference voltage, previous battery voltage, and voltage drop thresholds are all values needed for calculations. We also defined our original variables as false so that they could be updated each time. For the serial begin, we started by initializing our pins, so we set the inputs as inputs, the LED as an output, and the button as input pull-up for the pull-up resistor. Then finally at the end of this, we just have a slight delay and some Arduino debugging code. At the beginning of the loop, we first update our Arduino cloud variables, then we take an input for our light value from our LDR, and we print this to the serial monitor. We then take the raw value from the analog pin for the battery voltage. This is then calculated using the reference voltage to convert to the actual value to an actual voltage, and then voltage divider is used with the resistances to read the actual voltage value. This value is then updated in the Arduino cloud variable and printed to the serial dashboard. The grid disconnected dashboard value is the opposite as actual grid disconnected, as it wants to show green when connected and red when disconnected on the dashboard. The other Arduino cloud variables are then updated. Now we check for a voltage drop to show a grid disconnection. This less than 13.8 is to account for when the battery is fully charged and it's maintaining a charge. It'll never reach 13.8 if it's not connected, but if it is at that point, it'll fluctuate up and down, and we don't want to monitor that drop as an actual grid disconnection. Then we're going to actually monitor to see if the voltage drop is greater than 0.2 volts. If that's true, then the grid is disconnected, and we update these variables, and then we also check for a grid connection with a voltage rise. Then we check for the light value to see if it's less than 5, which is our threshold. If it is, then we rate high to the LED, which is flipping the relay by sending a high signal, and we update these variables. If the light value is not higher than the threshold, we will send a low digital signal, which will turn off the light. Then we will also have to make sure the LED turns off when a voltage rise is detected, so we will then send the low signal, which will turn off the light. And here we are updating variables for our next iteration. This is for the button. If the conditions are met that the light will be off, we'll be able to press the button and turn on the light, but that won't be an option if the light is already on, as we won't need to test. This is the thingproperties.h file that Arduino. Now that we know how the system works, we can observe the real components and see how they work. On the left of the box is the battery. The test input button functions by pushing in the case of a non-emergency, and it will turn on the light to ensure that the light is working and does not need to be replaced. When the LDR sensor is covered, we will see a drop in light values. Through many tests, it was decided that the best threshold for this light was 5. When the room light is below 5, in the case of an outage, the light will turn on. When we uncover the LDR, we will notice that the light values begin to go up as the room light is exposed again. The first set of resistors serve as the voltage divider rule for the battery voltage readings. As we observed in the code, the voltage is calculated through the resistor values and the reference voltage, to accurately display the battery voltage on the dashboard. The second set of resistors is the voltage divider for the LED. The relay and the Arduino are in the bottom of the box. As we could see, when the light turns on, the relay has a red LED which turns on, indicating that it is in the normally open position and is powering the LED. When the LED turns off, we will see that this red LED turns off as well. Each component in the box is secured with Velcro tape to ensure that nothing will move and that the box can be transported without worrying about anything shifting or breaking.